Alright, I got the hoarse voice going on. I don't know if I'll be able to talk tomorrow. I might not have a voice tomorrow. So I'm going to go ahead and do this presentation like this. Yeah, some people calls it a sore throat. I calls it laryngitis. So I'm talking about bones and how they're related to kidney problems. But here's the thing. Like, we got the one case that's different from every other bone problem that's caused by the kidneys. But I'm going to go over like the majority so we get the high yield stuff. And so I was actually supposed to cover what kind of kidney problems will cause bone problems. The answer to that question is every kind of chronic kidney disease. Every one of them. They all cause bone problems. So I'll just go through a little bit of it. Got the fibroblast growth factor whenever it increases, which is actually going to increase later. I don't know why I put this first, but it's going to cause a decrease in calcitriol, the activation of vitamin D. And I got right here about some stuff about hyperphosphatemia. In our case, we have hypophosphatemia. Like I said, we got the one case that's different from everything else. So typically, you're going to get hyperphosphatemia, and it's going to cause hypocalcemia. Now, there's three things that can activate PTH, and these are two of those things. Let's take a look at the hyperphosphatemia that you would normally get that we didn't. And we didn't get it because we have a proximal convoluted tubule problem. The entire portion of the tubule is damaged that reabsorbs phosphate. But typically, it wouldn't really be that portion of the tubule that's having problems. Typically, you'd have a decreased glomerular filtration rate, and that would cause less phosphate to be filtered across the glomerulus, and all of the phosphate that got filtered across pretty much would be reabsorbed. So the little bit that got across would all be reabsorbed. Now in the serum, the phosphate's going to bind to calcium, and that's the end of the show right there, because you're going to have no free calcium. So you get a low calcium, activate PTH. You get the calcitriol not being activated, activate PTH. You get the PTH, that phosphate will actually itself enhance transcription of PTH, so you get more PTH. Now, typically, PTH is going to cause phosphate to be excreted, but it can only do so much, and then it's at its maximum capacity to operate. PTH basically has a speed limit. It has a governor inside of it. It says, PTH, you can only go at 55 miles an hour. If you try to go faster than that, the governor kicks in and slows you down. So you can only secrete a certain amount. You can only cause a certain amount of phosphate to be excreted. You can't cause all of it to be excreted. No. So this is a big deal because this PTH is doing two things. We got all this extra phosphate. It's acting on the kidney to excrete that phosphate and to reabsorb calcium. But it's also acting on the bones to break down bones. What happens when you break down bones is you get basically, I don't know why that line went there. So when you break down the bones, you get calcium entering the blood. That's two pluses. And then you get also phosphate. So the phosphate will also be released from the bone. So you're trying to get rid of phosphate in the kidney, but your bones are giving you even more. And if you're at your maximum absorption, then you're going to end up exacerbating your hyperphosphatemia. So anyhow, we're gonna have more an exacerbated hyperphosphatemia, and we're also gonna have some bone remodeling going on. A few other things that happen is I talked about the FGF already. You also get skeletal resistance to PTH, and then you can get tertiary hyperthyroidism. So I was supposed to look at these, all the different diseases of the kidney that can cause bone problems. And they're broken down into 4 classifications, and each of these classifications has a slightly different pathology. Maybe it's completely different. I started reading like a 10,000 page book on this on Monday. It was like the whole book was called Chronic Kidney Disease, Bone Mineral, maybe I have this written wrong, Bone Mineral Disorders or something like that. But in all that reading, all that thousands of pages I did of reading, I found out this one thing. There's 4 types of these chronic kidney diseases, and they're classified by how they affect the bones. So I'll let you read it. I don't want to read it to you. But that's about all I learned from that book. So another thing I learned from that book is the bone problems and the growth problems are not the same thing. They got a completely different pathophysiology for both things, and so we want to take a look at the growth problems real quick. So I got a couple things written here. I got nutrition. I'm going to zoom in and, and talk about that real quick. So when we got nutrition, what I mean, and I'm not saying that she's not eating. That's not what I'm saying. I'm saying that she's urinating out protein. So that happens in some types of chronic kidney disease. And also, some kidney diseases can cause vomiting. So you're vomiting out your nutrients. Take, for example, diabetic ketoacidosis, which it can cause vomiting, and it can also cause kidney problems. So that's like another etiology that's causing the chronic kidney disease, but is also causing a nutritional loss. The thing you gotta know is, though, these things can't just be like, this is happening today and I got shorter. No, it has to be going on a long time, and it has to be going on in a growing child. And the main cause of growth issues in kidney disease is an interruption of the growth hormone IGF axis. Now, 2 things are going on in this situation. And so let's just go ahead and zoom in here. We'll write down some things going on. First of all, IGF stops responding. So it does not. So let's just put respond and put a circle. I didn't write that circle big enough. It does not respond to growth hormone. The other thing you have is you have decreased renal clearance. So decreased clearance of another protein called IGF-BP. This is the IGF binding protein. If you're not urinating that out, you're keeping it in your blood, that means you have a higher ability to bind IGF. So you're going to have less free IGF in your blood. Now there's one more thing I was not able to elucidate, and that is the fact that we're going to have increased hepatic production of IGF-BP. So for whatever reason, the liver decides, hey, I know blood's telling me I have enough, but you know what? Dang it, I ain't got enough. And then there's also something called non-renal abnormalities in growth. Now this is, I would say probably in our case, we got a little bit of this and we got a little bit of this. So if you're supposed to reabsorb proteins, at least the small proteins that get filtered, some small proteins get filtered, so you're supposed to reabsorb those in the proximal convoluted tubule. But we got PCT damage, so if we have damage, we're going to be peeing out proteins and amino acids, right? Everything in your body needs proteins and needs amino acids. But not only are you peeing out your proteins and amino acids, but you are burning them for fuel. Let me explain real quick what I'm talking about. Alright, so you got your urinating out, we'll just say you're peeing out glucose, right? But you got to keep your blood glucose up, else your brain will die. So what you do, you go into your liver, you say, liver, here's some proteins, and I want you to turn those into glucose. So you got the glucogenic and the ketogenic proteins, and so we're going to take some glucogenic proteins and make some glucose, and we're going to take some fat, and because the liver needs some energy to be able to do this, we're going to do some beta oxidation. So now, because we're peeing out the proteins straight out, and because the glucose get peed out, we're burning up the proteins to make more glucose, we got no proteins. Now also with cystinosis, Fanconi, the Fanconi cause cystinosis, or I'm sorry, the cystinosis cause Fanconi. Usually in those situations, you get a hypothyroidism. Now we did some T3, where we did some T4 hormones, and we did TSH, and they were in the normal range. Now here's the thing, Matt, I just want you to hear me out real quick. There is something called subclinical hypothyroidism. The definition of this pathology is that T4 is in range, but it's in the low side of normal. So T4 is in range, but TSH, this is what I looked at. It said that it's high, but it's usually less than 10, and it used like milli-international units per some volume. I don't remember what it was. Our TSH wasn't given to us in that unit, and I didn't take the time to look it up and convert it. So we might not have this subclinical hypothyroidism, but we also might. This is something that causes growth problems, and it's seen in cystinosis causes Fanconi disease. Alright, let's talk about the GFR now. The pathology of kidney, whenever you're looking at GFR, you're looking at basically how many nephrons are still working. That's what GFR is going to tell you. And so by knowing how many nephrons are still working, we can give major categories. Now this is only good for ages 2 and older, but these are the categories. If they got GFR greater than 90, they're good. Their filtration is either normal or is really high. I mean, they had a whole bunch of alcohol, these little 2-year-olds. I'm going to go ahead and let you guys know, based on the most recent mathematical calculations, we got a GFR that's at a G3A. And that's based on the updated Schwartz estimate equation. So I think I just said this. I'm not going to beat a horse. Now here's a picture that I copied from our textbook, and this is actually a Photoshop. So in this nephron, what is going on is we got volume coming out of here. Let me change this to black so we can see. We got some volume coming out of there. And we want to know how much volume. That's what GFR is telling us. It's giving me volume. How much fluid is being secreted out of the glomerulus into the Bowman's capsule as ultrafiltrate. The thing is, it's impossible to measure that because we can't come down here and measure what's coming out, because we don't know if what's coming out is what came across that capsule, because stuff can come in, stuff can leave, and so what comes out isn't going to tell me what came in there. But we got something called the law of conservation of mass. Basically what that says is that anything, not just liquid, but anything, so if a solid goes into this kidney, into this nephron, it has one option. It has two options. It can either stay in here or it can leave. And whenever it leaves, it got two options for that too. It can leave here or it can leave here. Now water, we can never know if we can never just measure it because it's always going to leave. But we might be able to find a solid, a solute, that cannot get excreted here and can't get sent in here. That way we'd say for every bit of that, for every gram of that solid that came across here, that every gram of it's also coming out here. We got to find one solid that does that. And as long as that solid is something that the kidney does not synthesize, so the kidney doesn't synthesize it in the tubule, and the kidney doesn't metabolize it, because so those are other ways that it doesn't have to leave as that same solute. It can leave as a different molecule being incorporated, but it does have to come in, it does have to leave. So this is the law of what goes in must come out. And that particular solid we use is called inulin, not insulin, but inulin. And you say, well, how does measuring a solid let me know how much liquid is coming across there? I'm glad you asked, because I can use a little trick called dimensional analysis. If I take the mass of something, divide it by the volume of something, that is the same thing as a concentration. So if I can measure the concentration of that solid in this blood right here, then I'll know the concentration of it that's getting filtered in here to begin with. Now, just knowing the concentration doesn't tell me anything, but if I take the concentration, which is a mass divided by a volume, and then I multiply that by the volume, which the volume we're talking about is the filtration volume, or the GFR. So this is the GFR I'm talking about. At that point, these two units cancel, and I'm left with the mass. Well, you say you still don't know what the volume is, so you can't cancel it. So far, you're right. But I can figure out what the mass is, because the mass that goes in is also the mass that has to come out. So if I do that same trick on the urine, so the mass of that solid that's in the urine divided by the volume of that urine is going to give me a concentration. If I measure the concentration in the urine, and then I multiply it by the volume of that urine, then all of a sudden I know the mass that went into the tubule. So now, out of all of these variables, I only have one that I don't know. Now we're going to play around a little bit more math and do something even better. So if I said that the concentration times the volume is equal to the mass, I did say that. And so if I say the concentration that gets filtered times the volume that gets filtered, which this will be my GFR, that equals the mass that was filtered. I'll just call that mass 1. And the concentration of the urine times the volume of the urine, that's also the volumes are going to cancel out, and that's going to give me the mass, which is mass 2. But we say mass 2 and mass 1 equal because mass can't be created or destroyed. And so now I can set these equations equal to each other. C1V1 equals C2V2. And this V1 is what I want to figure out. So I just take that concentration, number 1, and I divide it. And I get C2 times V2 over C1 is equal to the glomerular filtration rate. And see, this is an old chemistry trick. And so let me replace this with some letters you might be used to. So the GFR, that's my volume, is going to equal the concentration of a solute in the urine times the volume flow divided by the concentration of that substance in the plasma. Inulin costs a lot of money, and it takes a lot of time to do. Some people don't like to do it. And some people just think math is kind of interesting, kind of fun, and so they like to do math, and so they find mathematical ways to not do tests. What I'm trying to say is we can use the creatinine to calculate an estimated glomerular filtration rate. The reason we can use creatinine is because it comes from skeletal muscle and from food that you eat, but it goes into the blood basically at a constant rate. It gets freely filtered across the glomerulus and is not reabsorbed. It can be secreted though. So we're going to take a look at how to do this. And what we do, and I was going to do some more math here because there's some more cool math I can do, but I already got a lot of time going on to this lecture. So ask me on the side and I'll show you some even more cool math with this creatinine. So you can say that the clearance of creatinine is approximately the GFR, and this could be off by 10 to 40%. But to do the clearance of creatinine, you gotta remember you need to know the urine volume, because essentially we're saying the clearance is equal to GFR, and so the clearance or the GFR is going to equal the urine concentration of creatinine times the urine volume flow divided by the plasma concentration of creatinine. Or this is usually written as capital C SCR, serum creatinine. But remember, I'm lazy and I don't want to wait 24 hours collecting pee. Now, I don't know what happened to my slide here, but I had two different equations that were really good at solving for the GFR in adults, but they don't work on young kids very well, as I found out. And I can't show you those right now, but I have those in my study guide, and I also created an Excel spreadsheet I'm going to show you in a minute. I also wanted to show you this fancy Schwartz equation because it's the one that actually works with kids. This equation has been updated 3 times. Well, it's been updated 1 time. There's 3 versions of the Schwartz equation. There's the original 1970s version, and because our ability to detect creatinine has become better, now the old equation from the 1970s it was based on failed or flawed creatinine assays, and so it doesn't work anymore. So in 2008, Schwartz got back on the drawing board, and him and a team put together 2 new equations. The first equation is one that's useful at the bedside because it literally requires you to remember this number, find out the height, and find out the serum creatinine, and that works for kids. And then there's an even better one that it's not useful. So this one is useful at the bedside, and there's this way longer one, like 15 feet long, that I put on the study guide and I put in my PowerPoint, and it will calculate a little bit more accurate than this one. So I made some Excel spreadsheets, and the reason I did that is I wanted to have a resource in the future where I could just pull it if I wanted to calculate creatinine or calculate GFR from creatinine. But the thing was, the first one I did, it was an adult one, and I realized that like 2 minutes after I made this, so I decided to just go ahead and make all of them, and not just the kid one, but all the adult and everything. So this one was from like the late 1970s, and it's still good because it's easy. Like, this is an easy equation to remember, but it also requires you to do 3 more subsequent equations, and so that makes it suck. Because this equation will give you creatinine clearance, it will give you absolute creatinine clearance, or basically an absolute GFR, but you always have to normalize GFR to 1.73 meters squared of body surface area, because if you don't, then you won't be able to compare it back to that table and see whether or not they're in renal failure. Last thing I wanted to point out was this equation is made for adults, and it's made for adults, and it's made for people that are not obese. So that's the thing to remember about this equation when you look it up: adults and not obese. It calculated this little girl's creatinine clearance at 110, which is way above being normal kidney. And this MDRD equation, it was created by studying 38 to 63-year-olds, I think it was. And so whenever I plug her numbers into this, there's 2 different versions of this equation you can use based on updates that they've made to it. And my goodness, this girl's GFR is just outstanding. Now here's that Schwartz equation I told you that was good for kids. It's made for kids. And here's what you get from the bedside easy version. And here's what you get from the super advanced version. It's already normalized for you to 1.73 meters squared of body surface area. And so you don't have to do anything to come over here and compare it. You say, oh, this fits in right here, this fits in right here, so both of these equations are basically going to get me to the same result. I will point out, however, that this advanced version requires the cysteine, the cysteine C. I didn't see that in our lab reports, so I just threw in the number 1 because I found the number 1 being reported, 1 milligram per liter, reported on a lot of stuff, and so I just threw in the number 1. Now, the reason I just went ahead and went with it because it was so close to the other one. And I know why that's not evidence. That's, to me, that confirms something. I don't know what it confirms.